t is equal to pi over 4, where we said already sec squared t when t is pi over 4, that gives us 2. So 2 times 2 is 4. 1 over this, because we need the reciprocal, this gives us a quarter, and therefore this is equal to 2. And therefore we know that the gradient of the line L, which is the negative reciprocal of this, is minus a half, right? So that makes life easier, and you can see that this is exactly what we want, okay? So we're going in the right direction. Now, to get the equation in a straight line, we just need to know the coordinates of a point that this line passes through, and we know that the, P is the point when t is equal to pi over 4. So, we get the following, right? We have, x is equal to, so here, well, this is just 2 plus 1, okay, because tan of pi over 4 is just 1. And then here we already know, again, it's worth remembering this and working out in this question, that sec squared of pi over 4 is 2, so that's 2 times 2, 4. So 4 plus 3, which is 7, okay? So we have the coordinates of the point that it goes through is 3, 7. And then we can go ahead and just use, the following. So y minus y1, so minus 7, is equal to minus a half. And then x minus x1, so x minus 3. And putting this in, what do we have? We have y minus 7 is equal to minus a half x. And then we have here plus 3 over 2. And if we add the 7 to both sides, you get y is equal to minus a half x plus 17 over 2. So not too bad for the first part of the question there. So for the next part of this question, we're asked to show that all points on C satisfy this equation here. So this is going from a pair of parametric equations to a single Cartesian equation. And whenever you see tans lying about and sec squareds and cots, whatever, I would just have my reciprocal trig identities in the back of your mind, especially when you're doing this whole converting from parametric to Cartesian. And of course, the relevant identity here is going to be tan squared t plus 1 is equal to sec squared t. But why is this useful? Well, if I subtract 1 from both sides here and then square, what do I get? I get the following. I have that x minus 1 squared is equal to 4 tan squared t. And then over here, if I subtract 3, I have y minus 3 is equal to 2 sec squared t. So you can see here that, I'm basically setting up to use this identity, right? So that I can relate these two things and eliminate the dependence on t, because that's the goal, when you're trying to go from a pair of parametric equations to Cartesian. But here I have a 4 tan squared t, and you notice that, the coefficient of the tan squared and the sec squared in this identity is the same. So that suggests that I want to divide this by a half so that I have a 2 tan squared t and a 2 sec squared t. So let's go ahead and do that. So what do I have? I have a half x minus 1 all squared is equal to 2 tan squared t. And then you can imagine multiplying this through by 2. So I have 2 tan squared t plus 2 is equal to 2 sec squared t. And now I can just, again, get rid of my dependence on t by substituting tan squared t for something in terms of x and sec squared t for something in terms of y. And so what do I get? So I have the following. I have